Today we are going to see placing the third layer. Yesterday we have seen two layers. The orange one is A layer and the yellow one is B layer. After placing two layers, now we have got two types of voids. What are they? Tetrahedral voids and octahedral voids. Tetrahedral voids, octahedral voids. See, this is an octahedral void. You can see the hole through that. This is a tetrahedral void. This octahedral void, tetrahedral void, octahedral void, like that. So we have two options to place the third layer, either on all tetrahedral voids or on all octahedral voids. If you are keeping the bolts on all tetrahedral voids, then you will not be able to keep on octahedral voids. If you are keeping on octahedral voids or octahedral voids, then you will not be able to keep on tetrahedral voids. Only one option is possible. Suppose if we place on all tetrahedral voids on this, like this. Why am I keeping this orange ball? Because this ball is in alignment with that orange ball that is of this first layer, A layer. So I'm keeping an orange ball. Why? Because it is in direct alignment with the A layer. So I'm keeping on all tetrahedral voids. So this tetrahedral voids, this tetrahedral voids, this tetrahedral voids. So here one, this tetrahedral void, this tetrahedral void, like that. If I'm keeping the if I'm keeping the bolts of the third layer on all tetrahedral voids, then this octahedral void, see, you can see the gap. Octahedral voids cannot be filled. See, this is an octahedral void, this is a tetrahedral void. So all the tetrahedral voids are filled. So the third layer is exactly in alignment with the first layer. If first layer is called A layer and second layer is called B layer, then third layer is again called A layer. Fourth will be B layer. Then A layer, B layer, A, B, etc. Such 3D arrangement is called hexagonal close packing in 3D. First A layer, then alignment is different, that is B layer, then alignment is same. Alignment is same. See, on the tetrahedral void, here tetrahedral void, that time this octahedral void is not filled. When all the tetrahedral voids are filled, means after making the second layer, when all the tetrahedral voids are filled, you will be getting the same alignment as that of the first layer, that is A layer. So we call this third layer again as A layer. This third layer again as A layer. So AB, that will give rise to hexagonal close packing in 3D. Now go for the second option, that is on all the octahedral voids. This octahedral void, this octahedral void, this octahedral void. When I keep on all the octahedral voids, that gives an entirely new alignment. It is not matching with A layer, it's not matching with B layer, it's entirely a new layer. So I'm keeping another color like green. Green, here green, here green. So that is A, B, C. First is A, second is different alignment B, and the third is again a different alignment. See, if I keep on this octahedral void, it will give you a new alignment called C layer. So first layer A layer, second B layer, third is C layer, again fourth will be A layer only. So it will be ABC, 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 etc., which will give rise to CCP, cubic close packing, whose unit cell will be FCC. CCP means FCC only. So here ABC, 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 which will give rise to cubic close packing. AB, AB, AB will give rise to a hexagonal close packing. ABC, ABC, ABC will give rise to a cubic close packing. We call it as CCP, and its unit cell will be FCC. So CCP means FCC only. Whether it is HCP or CCP, both are equally efficient. Both are equally efficient. That is 74 percentage of the unit cell will be filled with the spheres, atoms, or balls. So whether it is HCP or CCP, both are equally efficient, 74 percentage efficiency. And coordination number is also the same. If you consider the coordination number in HCP. Look at an interior ball. See this one. This is in contact with 6 balls in its own layer and 3 in the A layer. In the A layer, you can see through this 1, 2, 3 in the A layer, and 3 will be in the front. See, if I'm keeping on all the tetrahedral voids, 1 will be here, 1 will be here, and 1 will be here. So it will be in contact with 3 balls in the C layer. 1 ball here, 1 here. See, 1 here, 1 here, 1 here. 1 is here, tetrahedral void, tetrahedral void, tetrahedral void. So it will be in contact with 3 in C layer. In its own layer, in its own layer, 6. From A layer, 3. From C layer, 3. So altogether, this will be in contact with 12 balls, 12 spheres, 12 atoms. Same is the case with this one. 6 in its own layer, 3 behind, 3 in C layer, front layer. So its coordination number is 12. Whether it is HCP or CCP, the packing efficiency is 74%, means equally efficient, and the coordination number is also same, that is 12. So that's about close packing in 3D. Now, if n is the number of atoms to make this crystal lattice, bigger atoms, then there will be twice n is the number of tetrahedral voids. Suppose there are 100 atoms, there will be 200 tetrahedral voids and 100 octahedral voids. That means if n is the number of atoms in this crystal lattice, there will be 100 if n is the number of the atoms in this crystal lattice, there will be n octahedral voids and 2n tetrahedral voids. That means total number of voids will be 2n plus 1 n, that is 3n. Once again, if capital N is the number of these atoms in this crystal lattice, there will be twice n tetrahedral voids and n octahedral voids. Sometimes only the tetrahedral voids are filled, sometimes only the octahedral voids are filled, sometimes some of the tetrahedral voids and some of the octahedral voids are filled. Sometimes only a fraction of this tetrahedral voids are filled or a fraction of the octahedral voids are filled. Depending upon the questions, you have to find out the molecular formula. Once again, if n is the number of atoms in this crystal lattice, there will be twice n, 2n tetrahedral voids and n octahedral voids. Suppose there are 1 mole of atoms there will be 2 moles of tetrahedral voids and 1 mole of octahedral voids. Based on this, we'll be doing some numericals. Question. A compound is formed by a compound is formed by 2 elements X and Y. The atoms of element Y, the atoms of the element Y as anions make CCP and those of X occupy all octahedral voids. What is the formula of the compound? A compound is formed by 2 elements X and Y. The atoms of element Y make CCP. Atoms of element Y make CCP means I'm drawing a CCP. CCP means FCC only, so I'm showing an FCC. So here, one atom at the corner, 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 corner. This corner, there are 8 corners. From each corner, the contribution it's only 1/8. This is 1/8, 1/8, 1/8, 1/8. From here 1/8, from here also 1/8. 2, 4, 6, 8. So 8 into 1 by 8. 8 into 1 by 8 is 1. So atoms of Y means there is only 1. Y is 1. What about X? X occupy all the octahedral voids. X occupy all the octahedral voids. How many octahedral voids are there? How many octahedral voids? If 1 is the number of these atoms, octahedral voids will be 1 only. If 1 is the number of Y atoms, the atoms of element Y make CCP and those of X occupy all the octahedral voids. Here I have taken one unit cell. You can take the entire crystal also. For example, Y is equal to, let Y be N. Then X will be N. X will be N. So this N will get cancelled. YX, but we won't write YX because, for example, when you write NaCl, Na plus Cl minus, cation is to be written first. The small atom is to be written first, or small ion, that is cation, is to be written first. So we'll be writing X first, then Y. So here you'll be writing XY. Either you can take the unit cell or you can take the total number of atoms. If Y is equal to N, how many Y? Ny. N atoms of Y, then there will be N atoms of X. So here I have taken the entire crystal lattice. Here I have taken the unit cell. Unit cell quality, the specialities of unit cell is the same as that of the entire crystal lattice. If Y is equal to N, there are N Y atoms, there will be N X atoms. So X N Y N. This N will get cancelled. So the formula will be XY. Next question. Atoms of B. Atoms of B form HCP lattice. Whether it's HCP or CCP, the packing efficiency is the same. Whether it is HCP or CCP, if capital N is the number of atoms present in the crystal lattice, there will be 2N tetrahedral voids and N octahedral voids. HCP lattice, and those of element A, those of the element A occupy 2/3 of tetrahedral voids. 2/3 of tetrahedral voids. Tetrahedral voids. What is the formula of the compound? What is the formula of the compound? This is the question. Atoms of B form HCP lattice. Suppose there are NB atoms, and those of element A occupy 2/3 of the tetrahedral voids. Element A, there should be how many tetrahedral voids? 2N tetrahedral voids. But all tetrahedral voids are not filled. Only 2/3 of the tetrahedral voids are filled. So here N will get cancelled. Here it will be A 4/3 B. But we don't write the formula like this in whole numbers. To make it whole numbers, nearest whole number, what you have to do? You multiply each one by 3. So I'll be multiplying all these things A and B by 3. How? Into 3 into 3. So the formula will be A4 B3. Whole number. This is the formula. Next question. A compound forms HCP structure. What is the total number of voids? What is the total number of voids in 0.5 mole of it? How many of these are tetrahedral voids? How many of these are tetrahedral voids? A compound forms HCP structure. So if N is the number of atoms, big atoms, how many octahedral voids will be there? Octahedral voids? N. How many tetrahedral voids will be there? 2n. And they said if n is the number of atoms in that crystal lattice, for that n they have given the number 0.5 mole. 0.5 moles. So how many octahedral voids will be there? 0.5 mole. How many tetrahedral voids will be there? 2 into 0.5 mole. That means 1 mole. What are the total number of voids? So this and this, that is total number of voids will be 1.5 mole. How many of these are tetrahedral voids? See, 1 mole. 1 mole will be out of this 1.5 mole. 1 mole will be tetrahedral voids. So this is the answer. First answer is 1.5 mole. Second answer is 1 mole. Now you know that 1 mole is equal to 6.022 into 10 to the power 23 particles. Either you can write in terms of particles or you can write in terms of moles, because they just ask how many of this. If you are telling in terms of moles, it's somewhat like dozen. You said dozen. In that way, you are telling 1 mole means 6.022 into 10 to the power 23. 1 dozen means 12 particles. So either you can talk in terms of moles or you can talk in terms of the real number of particles. Next question. A solid with cubic crystal. A solid with cubic crystal is made up of two atoms. Is made up of two atoms, P and Q. P and Q. Atoms of Q are at the corners of a cube. Are at the corners of a cube. And P at the body center. What is the formula of the compound? What is the formula of the compound? A solid with a cubic crystal means CCP is made up of two atoms P and Q. Cubic crystal, cubic close packing. So the unit cell will be FCC only. Atoms of Q are at the corners of a cube. Now let's see this cube. Atoms of Q are at the corners of a cube. So I'm going to draw a cube. Q at the corners. Cubic close packing it is. So from each corner it will be 1 by 8. 1 by 8. 1 by 8 like that from each blue 1 by 8. So the number of atoms of Q, that is 1. 1 by 8 into 8, 1. And P at the body center. P at the body center. So its contribution is 1 full. So here P. P1. So what is the formula of the compound? Formula of the compound will be PQ. So once again, a solid with cubic crystal is made up of two atoms. So one cubic crystal, cubic form I have made. Atoms of Q are at the corners of a cube. This is Q. That is Q, Q. Blue ones are Q. 8 corners. So from 8 corners, total number of particles will be 1. What is the formula of the compound? Formula of the compound. So Q1, how we got this 1? 8 into 1 by 8. 8 into 1 by 8. So that is 1. And this P, sender 1. This one is P. Its contribution is full. Its contribution is full. So that we are writing as 1. Here 1. So the formula will be PQ. Thank you.